Welcome back, and today I'll be covering the second fundamental theorem of calculus. And before I do that, I'm going to discuss what an antiderivative is, also known as an indefinite integral or primitive integral of f of x. So we say capital F of x is an antiderivative of f for x in an interval a comma b, if and only if the derivative of capital F gives you f. So it's a pretty simple statement. It's just saying if we differentiate the antiderivative, we get the original function. And here's our notation, kind of. Okay? So we have, of course, our integral symbol here. Now remember, there is no upper or lower limit. This is known as indefinite integration, and we only have this line. Okay? And this is not the same thing as the Riemann integral, by the way. They are different, okay? They are completely different concepts. So this takes the antiderivative. The other one is like adding up a bunch of tiny rectangles. So of course, the functions inside is called the integrand. This dx tells us what variable in respect to, like in this case, it's x. And the antiderivative is our answer plus some constant of integration because, of course, if we take the derivative, we get f, but the derivative of a constant is 0. So if you add a constant, you don't change the derivative, right? You have to take that into consideration. So here's an example. All right, say we want to compute what this k dx, okay? Well, this is kx plus c, right? And the reason why is because uh, in order to get a constant, we have to take the derivative of a line, right? And this line is kx plus c. So when we take this derivative, we get k. So we've checked. So to sum that up, if when we take the derivative of our antiderivative, okay, plus the constant, if we get the integrand back, then our antiderivative is correct. So here's an example. Compute the integral of x cubed dx. So for derivatives, the power rule decreases the exponent by 1, and we'll expect anti-differentiation, the inverse, to do the opposite, okay? So is the antiderivative of x cubed dx x to the power of 4? So we'll check, okay? So x to the power of 4, prime is equal to 4x to the power of 3. So the antiderivative of 4x cubed dx is x to the power of 4. But, this isn't what we're looking for. We're looking for x cubed. So in order to get rid of the 4, we may divide x to the power of 4 by 4. That way, when we drop it down, the 4 and the 4 cancel out. So does this work? Okay, so we'll check the derivative of x to the power of 4 over 4, which is our antiderivative, gives us this. The 4 and the 4 cancel out. We get x cubed, which is our integrand. So we know this holds true. So we now can create a general reverse power rule. And this is our theorem, right? For p, in the real numbers, the only exception is p cannot be -1. If p is -1, that is the antiderivative of 1 over x dx. That's a whole other deal with natural log. That's its own thing. But if it's not -1, then we can just do this reverse power rule, which we add the exponent by 1 and divide by our new exponent, okay? So let's see. So we'll prove it, and it's actually quite simple. We just use power rule to differentiate. We drop down this, and the numerator and denominator cancel out, and we get our integrand. So remember, for the derivative, we drop the exponent and subtract by 1. For anti-differentiation, we increase the exponent by 1 and divide by the new exponent. And also notice that anti-differentiation is linear, right? And it follows by the linearity of derivatives. So here's an example of what we want to compute. The antiderivative of 3x to the negative 1/2 plus 2x to the power of 5 dx. So in this case, we'll take 2x to the power of negative 1/2, add 1, and divide by negative 1/2 plus 1. Now here we get 2x to the power of 5 plus 1 and divide by 5 plus 1. And of course, do not forget the constant of integration. This becomes 3x to the power of 1/2 times 2 because we're dividing by 1/2, plus we get 2 over 6, so 2x to the power of 6 over 6. And you can simplify this, but this is good enough, plus c, never forget that. Okay, now that we kind of have a good idea of what anti-differentiation is, at least the basics, we're ready for the second fundamental theorem of calculus. This is the theorem. If f is Riemann integrable on the interval c comma x, and for all x in c comma x, f prime of x is equal to f prime of it. Sorry, capital F prime of x is equal to f of x, or you could say for all x naught, I'm just saying that any point inside the interval, right, the antiderivative holds, right? Then we can evaluate the integral from c to x of f of t dt. Remember we said this was an area function? Well, this integral just becomes the antiderivative of x minus the antiderivative, sorry, capital F of x minus capital F of c. And remember, like we said, capital F is the antiderivative of f. So we can prove it. And we don't actually need the power rule. I just wanted to show you that so that we could do some examples later on. But all you need to know is what an antiderivative is for this proof. So we're gonna prove that for all greater epsilon greater than 0, this inequality holds true, which is to say we can make all of these, so specifically this minus this, we can make their difference the distance less than any positive epsilon for some partition Q. Now, since we know f of x, which is f capital F prime, is Riemann integrable, we have a partition Q, which we'll define as follows, such that we have that the distance between the upper and lower sums can be made than any positive epsilon. Since x is equal to x sub n and c is equal to x naught, right, our left and right endpoints, we have that the difference, remember at the beginning, capital F of x minus capital F of c is capital F of x naught, or capital F of x sub n minus capital F of x naught. Here's where we think. Where have we seen this before? And the answer is it looks like a telescoping sum, right? And it's this sum specifically. And the reason why that's important is that this sum sort of, it doesn't, but it kind of looks like we might be able to use it to resemble an integral. So we might want to work with that, but we'll come back to that. Just remember that. Since capital F is differentiable over the interval, and of course continuous over the closed interval, the mean value theorem can be applied. So this does the heavy lifting, the mean value theorem. It's a very important theorem in calculus, right? So we can specifically apply over the subintervals, right? So we have in any subinterval, right? Capital F of x sub I plus 1 minus capital F of x sub I over x of x sub I plus 1 minus x sub I is the derivative of capital F at di for some di, right? Some tagged point. We don't know what point it is, but some point in the subinterval, right? And remember, obviously, capital F prime is just F. Then by multiplying by x sub I plus 1 minus x sub I, we get this. But of course, we can just take the sum, right? And we still get the same thing because these two sequences are the same, their sums are also the same. Um, and the key thing to note here is that when we take this sum, we know this, we already said up here was just this difference. And this, believe it or not, is the form of a tagged Riemann sum. So if you learn the Riemann sum as a tagged in a tagged form, right, as long as you replace capital F prime with F, you're just saying that this is a tagged Riemann sum. If you don't know that, that's fine. It's just saying any D sub I, any rectangle we can create, any partition. It's a more general form of the Riemann sum, which Bernard Riemann first came up with. But if we're using the Darboux integral, which is what I've been using in these videos, I'm going to show that not that they're equivalent, but of course, how we can show this holds true, the fundamental theorem of calculus, right? So indeed, we know that the infimum, and of course, if we take this definition to be the Riemann integral, then we're done with the proof, basically. But we know that the infimum of this and the supremum of this are both less than and greater than just this, right? Hopefully, it's not too difficult to see. The infimum is a lower bound and the supremum is an upper bound. And remember, we came up with the notation P sub I for the infimum and S sub I for the supremum, and we'll multiply by x sub I plus 1 minus x sub I. And here's where we start to take shape, all right? Remember up here, this looks like a Riemann sum. Now things are starting to take a lot of shape, okay? Specifically, we can take our sums here again, and the key thing to notice here is that this sum, we already said up here was at capital F of x minus capital F of c. This left side is just the lower Riemann sum. This right side is the upper Riemann sum. And we know that the actual the definite integral is always going to be above the lower sum, but below the upper sums, right? That's kind of how we wanted to define it, and we can show that's true. Thus, we know as well, since it's Riemann integrable, we can make the upper and lower sums, their distance smaller than any positive epsilon by choosing um, uh, some partition Q, right? So we know that if we can make the upper and lower sums as close as we want, then whatever's in the middle, which happens to be capital F of x minus capital F of c, and the integral will also be squished together. We can make those distances less than epsilon, right? Think maybe, you might want to think squeeze theorem sort of in a way, but basically we're going to squish them together. They're going to be squished and they're going to be forced to be less than epsilon. But we already said this is the same thing as saying that the integral from c to x of capital F prime of t dt, which is just the integral at the beginning, is this. This is our result, okay? And this is the proof for the second fundamental theorem of calculus. And it really started to take shape the second we had this form of a tagged Riemann sum. And then from there, the rest was it was trivial. The main thing, of course, happened to be the telescoping sum and applying the mean value theorem over our subintervals. Now we're going to go over some interpretations and also some other things we can get, um, before we can just start using the second one fundamental theorem. We need to understand it. First is a pretty obvious, it's a pretty obvious result that we can compute any Riemann definite integral if we know an antiderivative of the integrand. So suppose we know the antiderivative of f dx is capital F of x plus c. This is our general solution, right? We're adding a constant because taking the derivative just gives you a zero and it cancels out. Right. This is our general solution, right? Now, of course, we could choose C to be anything because we said for any antiderivative, not just the general solution, but if you plugged in the general solution, right? So we wanted to evaluate the definite integral from a to b of f of x dx, and we plugged in our antiderivative. Notices the C would cancel out. So it's the same as we chose C to be zero, so we don't actually have to add a constant when we're doing the definite integral. And more importantly, when we have this integral, we can always evaluate it using the antiderivative. And that's the main, um, how do you say, main thing that we can get out of the second fundamental theorem. But it's way more important than just that. Another thing we can, hopefully notice is that any two antiderivatives differ only by a constant. So this entire time we've been talking about antiderivatives and we've kind of been assuming that, oh yeah, well, we can just add C and our problem's done. Any two antiderivatives, they will always differ by a constant. And we don't know if that's true, so let's show it. So we know if capital F and capital G are antiderivatives of F, then f of x, capital F, is equal to capital G plus C. Can we show that? So since their derivatives are equal, right, then by linearity of derivatives, the derivative of their difference is also zero, which is to say the derivative of their difference is zero means we can apply the mean value theorem and say, you know, if you want to think about it a bit more, through, of course, you may want to write it out similar to the monotonicity implies. Sorry, yeah, positive or negative derivatives imply monotonicity. The zero derivatives imply constant functions. So we know now capital F minus capital G is some constant C. So we've proven what we wanted to show. Um, and now we know kind of how we can write any indefinite integral. Just add that constant of integration and we're fine. This third interpretation is rather important for FRQs. So that is that the integral from c to x of f prime of t, so remember f prime is the rate of change of f, So it is saying that the accumulation of the rate of change of f in the interval is just the net change of f in the interval. I cannot explain just how important that is and how much you'll be using that, but it's very important. For example, in rectilinear motion problems, if you have the velocity, which is, of course, the derivative of position, well, the integral will give you just the different, the what, disposition, right? Yeah, I forgot the word. So finally, we're going to get a bit of a taste, but obviously not completely, into differential equations, ordinary differential equations, of course. Existence and uniqueness of a solution to an ordinary first degree linear differential equation. Don't worry if it's a mouthful. We'll talk about this in more detail later. So if f is continuous over some interval, we have an initial value problem, okay? Let's say we know the derivative of some function y of x, and we know some initial value at x naught, which is y naught. We are trying to find a solution y of x such that it satisfies our initial condition, okay? Of course, we have a general solution, right? We should be able to find the general solution by taking the antiderivative. But if we want to find the specific solution, the particular solution is the more technical term. If we take by the second fundamental theorem of calculus, if we compute this integral, we get this difference. So we get y of x is equal to y of x naught plus this integral right here. And of course, we do happen to know y prime is f. So as long as we can, figure out this number, it's a constant, we can figure out the particular solution for what y of x should be. And also, don't forget this formula because you will be applying it in FRQs. It's rather important. And here I'm going to zoom in to kind of give you an idea of what the graphs might look like. All of these curves differ by a constant, so all of their derivatives are equal, okay? But notice there's only one curve specifically that goes through the point x naught comma y naught, and that is the curve that we are looking for, okay? That specific function is the one that we are looking for. And here's our final ending example. Compute the integral from 0 to pi of sine of x dx. Previously, we did not have enough tools to do this, but now, using the second fundamental theorem, we note that negative sine of x is the derivative of cosine, right? So obviously, we're going to forget about sines and constants and just think, which function's derivative is sine? Well, cosine's derivative is negative sine, so negative cosine's derivative is just sine, which is to say the antiderivative of sine of x is negative cosine of x plus c, but remember we could just say c is 0 only for the definite integral, right? Because they'll end up canceling out. It doesn't matter. We just need to choose an antiderivative. So of course, when we compute this, here's a notation that you might want to get used to. This little bar here from pi to 0, this is the notation for, hey, we're going to take this function, plug in it at pi, subtract it by the same function evaluated at 0. And it's especially useful for definite integration. And when we do so, we're just going to get this. Hopefully, you know your trig, and you get that the integral is 2. A seemingly difficult problem simplified tremendously. So this theorem has a lot of applications and it's very important and you need to be sure to know it by heart if you want to do well in calculus. So good luck studying.